right. Hi, everybody. Screencast needed to wake up a little bit before we could get going here. Um, I am getting going on your tests, but one of the things that I found that's really slowing me down is that there were some people that forgot to submit their work. So I'm just going to read the names off here. I already sent out emails, but I checked this morning and only a couple of people had submitted it. And you can just go in and submit your work through Schoology because I have to have that work to grade your test. That would be Matt Alexander, Bill Gleason, Josh Meister, Mason Pearson, Jackson Tesser, and Avon Tao. I need to have your work from this hour for your test. So don't stop and do it right now. If we have work time at the end of the hour, go ahead and put your work in there because you have to show your work in order for me to give you the points that you earned. So yesterday we worked on simplifying square roots because today we're going to start the process that we're going to use in the last three sections here when quadratics, so something with an x squared in it, when they're not factorable. What do we do? Because in math there are two really basic rules, and the first one is we never give up. So if something has a solution, we're going to find it. And the second is there's no crying in math. So we're going to find them, and we're not going to cry. So completing the square is one of those ways that we can solve all quadratics if we know what we're doing. So we're going to solve equations by completing the square, and then tomorrow we should probably get to the rewrite functions by completing the square. Today we're going to focus on what's this completing the square business anyway. Well, it comes from what we already know how to do. The reason we have to have you look at so many different ways of factoring and practice so many ways of factoring is because we have to be able to use these processes for other things. And so when I see x squared plus 8x plus 16, I think, well, there's no greatest common monomial factor, but maybe this is one of those perfect square trinomials because that's x squared, and this is 4 squared, and if I take x times 4 and double it, well, look at that, I get 8x. So this can be written as one binomial squared, and that would be an x and a 4, and then we just look for the sign between the first and second terms to see what are those middle terms supposed to be, and in this case they're positive. Now, why do we have to know that pattern? Why can't I just say, hey, there's two numbers that multiply to 16 and add to 8. That's 4 and 4. Why can't I just write it like this? Isn't that the same thing? And the answer is yes and no. This would, with FOIL, multiply to give you x squared plus 8x plus 16. But you are missing a really big concept if you don't recognize this as a perfect square trinomial. And we need that perfect square trinomial pattern today when we start talking about completing the square. Because what we're going to do today is we're going to design these. We're going to be the ones that write the perfect squares. So now I have to think about this process backwards. Let's see. To figure out if this worked, I had to take the square root of both of these, and then I had to multiply it by 2. So if I'm going to undo that, I'm going to have to take that middle term, b, I'm going to have to divide it by 2 to undo it. And then instead of square rooting, I'm going to have to square it. And that makes it so that you don't have to memorize that little formula b over 2 squared. If you have a really good understanding of how to factor a perfect square trinomial, all you have to do is think backwards. Okay, normally it's square root and multiply by 2. So now it's going to be divide by 2 and square. And again, you won't need to memorize. So, perfect square trinomials, big, big deal. I take a look at b, x squared minus 6x plus 9. Well, obviously, that is x squared. And this is 3 squared. I multiply those two together. I take it times 2, 3x times 2 is 6x. I've got it. I know that this is a perfect square trinomial. So the x will go in the front and the 3 will go in the back. And then I look between the first and second term and I see the middle terms are supposed to be negative. There it is. This next one, little more complicated, bigger numbers. So again, we should look and say, is there a greatest common monomial factor? Something I could factor out of all of these. 4 comes out of these two, but it won't come out of the 25. And at that point, the 25 catches your attention, and you say, well, this is 2x squared, and this is 5 squared. I wonder if this is one of those perfect square trinomial thingies. 2x times 5 doubled. Well, 2x times 5 is 10x. 10x doubled is 20x. Hey, it is. It's one of those perfect square trinomials. So again, I can write it as something squared. And that something is the 2x and the 5. And then our middle term is positive. So 2x plus 5, the quantity squared. Now, like I said, our objective to complete the square today relies huge on us being able to design perfect square trinomials. It shouldn't be a hard process if we were really good at the factoring piece. So now, why do we want these perfect square things anyway? Well, like this says, sometimes we can just do solving by finding square roots. And it asks us, what is the solution of each equation? So when I look at these, the first question I'd have is, why aren't I factoring these? I mean, why do they say solve these by finding square roots? Shouldn't we be factoring? And I need you to notice that there is no x to the first term. So if there isn't an x to the first term, sometimes we can just solve it, which means we isolate the variable. So for 4x squared plus 10x equals 46, we'll subtract 10 from both sides. Still don't have the variable alone. I have to divide both sides by 4. And then to undo squaring, we take the square root. But whenever we physically write down a square root symbol, we have to put the plus or minus on there. And the square root of 9 is 3. So this one actually has two solutions, positive 3 and negative 3. Both of those, if we put them back up in here for x squared, will work. Watch. If I put a 3 in here, it doesn't matter if it's positive or negative. I'm going to square it and get 9. 4 times 9 is 36, and 36 plus 10 is 46. It's going to work. So I want you to look at B. And I'd like somebody to unmute, please, and tell me what step 1 would be for B. Exactly. What is step 2? Divide both sides by 3. And the last step? Take the square root of both sides. So x equals plus or minus. Now I have to do a little thinking. 10. Do any of our perfect squares? Oh, I should remind you, you want your little bookmark thing of your perfect squares out today. We'll be talking about those every once in a while. So do we have any nice perfect squares that will divide into 10 evenly? 9 won't go in there. 4 won't go in there. And those are the only two that are small enough that we could even consider them. So we're going to have to leave this the square root of 10 because that's a perfect answer. As soon as we grab a calculator, we're going to be rounding. And we don't want to do that. We want perfect answers. Most of what we do in algebra, the steps that we follow are so that we can find perfect answers. Now, if this truly were something you're using in the real world, you're not going to walk into Menards and say, I need the square root of 10 feet of that. So yeah, we do need to know that it's a decimal and we can get it on the calculator. But in math, we like to see the perfect answers. All right, got it. A. I need step number 1. Somebody please unmute and give me step 1. Somebody else. Beautiful, even before I was able to get it out. Next step. Take the square root of both sides. And as you watch your hand making that square root, train yourself. Oh, that means I have to do the plus or minus thing. Square root of 5. Well, 4 is the only number that's even smaller than 5, and that's not going to go in there. So that's done. We can't simplify the square root of 5 anymore. Alrighty, got it B, please.
Subtract 9.
Subtract 9 from both sides. Then
divide by 2 on both sides.
And to finish it up, square root of both sides. Well, we're not going to be able to simplify the square root of 2. We don't have any perfect squares that are small enough to divide into that evenly. Our first useful perfect square is 4. So that's not working. So what's the purpose of these? Because I didn't say, now we will complete the square. Well, the purpose of these is to show us, hey, if you don't have a middle term, then you can just take square roots to solve these. And it becomes kind of an easy process. So we would love this to happen. We would love to have something squared equals a number, and we solve it from there. But our job is now to make the something squared. That's where we'll use completing the square as a process. So this says we're going to solve a perfect square trinomial equation. And it asks, what is the solution of x squared plus 4x plus 4 equals 25? Now, if this had been a factoring problem, we would subtract the 25 and then we'd try to factor it. But that's not what this section is about. This section is about us figuring out those that couldn't be factored. So as we go through this, don't try to use your old skills. Some of them will be factorable, some of them won't. If it says by completing the square, we have to form a perfect square trinomial. Now, we're doing baby steps, so they actually are giving us a perfect square trinomial to start with. This is x squared. This is 2 squared. And if we take x times 2 and double it, we get 4. 2x times 2 is 4x. So this is x plus 2, the quantity squared. Now here's the connection they want us to make. Do you see how we have something squared on one side? Well, we just learned in the last 4 problems that to undo that, you take the square root. Well, that's what we need to do. So now we'll have x plus 2 equals plus and minus, what's the square root of 25?
5.
Yes. We're not done, but boy, did that just make the math a lot easier. We're not done because we have 2 equations here. We have x plus 2 equals negative 5 and x plus 2 equals positive 5. But those are some pretty easy equations to solve. We'll just subtract 2 from both sides and get negative 7. Subtract 2 from both sides and get 3. Both of those are solutions. If we put them back up into the original equation, they will give us 25. They're checkable. We can see that. So now I start thinking, well, they set this up really, really nice for us. Is it always going to be a perfect square trinomial? No. Eventually, because we know this, we learn a chunk of information and then they take something away. So eventually we have to figure out what numbers will make that work. But today we get a little head start that they help us with. So this says, what is the solution of x squared minus 14x plus 49 equals 25? Now, I want you to factor the left side, please. And when you're feeling confident, you can unmute and tell me what you have.
X minus 7.
Yeah. This is x squared. This is 7 squared. 7 times x doubled is 14x, and it has a minus in the middle. So, again, we have to look at this a little different and say, okay, I don't want to multiply that out. I want to take the square root. And I know the square root of 25, it's 5. So x minus 7 is going to equal plus and minus 5. Well, that means x minus 7 equals negative 5, and x minus 7 equals positive 5. And we have two very basic one-step equations to solve. So we'll add 7 to both sides. And we have x equals 2 and x equals 12. And again, if we wanted to take the time, we could put those numbers back up here in for x, and we would get 25 from the other side. So far we learned a chunk where they're saying, hey, taking square roots, if you don't have a middle term, an x term, that's a cool way to solve these. And then they upped it a little bit and said, all right, now here's what we really want. We want to have a perfect square trinomial equal to a number, and then use square roots to solve it. So now we're going to make them. We're going to design them. Completing the square. You can form a perfect square trinomial from x squared plus bx, we have to know what b is, by adding b over 2 squared. That's why I said when we started today, it's so important that we know those factoring patterns, because this is using the factoring pattern backwards. Instead of taking square roots and multiplying by 2, we're undoing it. We're dividing by 2, and then we're squaring. So this one says, what value would complete the square for x squared minus 10x? And you can either memorize the formula, or like I said, you can think back about the factoring. Most people memorize that formula. It's so little. I mean, most people just say, okay, I need b over 2 squared. That's what I need. So b is negative 10. So we follow the order of operations and we do what's in the parentheses first. Negative 10 divided by 2 is negative 5. And then we square it. And it's negative 5 times negative 5, which is positive 25. Now, if you're going to use your calculator for these, make sure you use parentheses whenever you do that squared piece. So these are little prompts here to help us with this. We know that b is negative 10. We know we have to find b over 2 and square it. We know we have to follow the order of operations. And we got 25. Well, now I want to see that. I want to make sure it works. So let's see. They said it's x squared minus 10x, and we just said the number that would make that work is 25. Let's check and make sure. This is x squared. This is 5 squared. 5 times x doubled is 10. Hey, it works. So that little b over 2 squared piece is what helps us to find the number that will make it a perfect square trinomial. So let's try this one. X squared plus 6x. Somebody unmute, please, and tell me what 6 is. Oh, God, I hate it when I do that. I just gave you the answer. Don't tell me what 6 is. All right, so why don't you go ahead and do b over 2 squared, and let's see if we all get the same thing. Not so bad, right? Finding that number to complete your perfect square trinomial. Well, they work out super nice if your b value is even, because when you divide an even number by 2, everything works out all pretty. But we are going to have fractions. Real life has fractions. That's just how it is. So b says, what value completes the square for x squared minus 5x? So this time I'm going to say it right. Somebody please unmute and tell me what b is. Good. So there's our negative 5. And here's our problem. Negative 5 divided by 2 cannot be simplified to an integer. But it's not that big a deal. I mean, you could always use your graphing calculator to square it, or just write it out twice. And with fractions, you always do top times top, bottom times bottom. So just because it turns out to be a fraction doesn't mean that it's going to be some awful math. It's not. It's still just b over 2, the quantity squared. So this one would look a little strange, because what we're saying is we just found the number to put back here for c that makes this a perfect square trinomial. So checking this one, we'd have x and 5 halves. So multiplying it, we'd have 5 halves x times 2. Well, remember, 2 is like 2 over 1. These 2's are going to cancel out, and we'll get the 5x. So it works. It's perfect. It's exactly what we needed. b over 2 squared gives us that perfect square piece. Now, the real reason that we have for the second objective for tomorrow is because it's supposed to make graphing lots easier. So I want you to see, I'm going to remind you how we just did all of our graphing when we were taking this last test. When something is in standard form, I want to remind you of all the math that we had to do to figure all this out. So we started with a formula, negative b over 2a, that we had to memorize. And then we went up here and said, okay, it'll be the negative of negative 8 over 2 times 2, because a is 2. That'll be 8/4. All right, my axis of symmetry is at x equals 2. That's also where my vertex is going to be. It's going to be at 2 something. And to find the something, we have to plug the 2 back up in here for both of these x's. So 2 squared is 4. 2 times 4 is 8. 8 times 2 is 16. 8 minus 16 is negative 8. And negative 8 plus 3 will be negative 5. So our vertex is at 2, negative 5. Well, that's definitely not a parabola. So then we figured out, well, I'm going to need some more points. I've got to have some more points. That definitely is not enough. I could put in 0 and 1. Those are pretty close to my axis of symmetry, and they're really nice numbers. 0, 0, 3. Oh, yeah. 0c. That always works in standard form. You put in a 1. 1 squared is 1. 2 times 1 is 2. 2 minus 8 is negative 6. And negative 6 plus 3 is negative 3. So we have 0, 3 and 1, negative 3. But we also have an axis of symmetry. So we can go equal but opposite on the other side and draw ourselves a really nice parabola. So tomorrow, what we're going to do, the next part of our objective, is to take a standard form, quadratic, and put it into vertex form. Because remember, vertex form has that perfect square in it. So that fits right in with our objective of completing the square today. That's it for today. This is enough to get us a good start and start to remember that b over 2 squared formula. So there's your homework. And I want to remind these people that you need to take some pictures of your work for the test and submit it through Schoology. Matt Alexander, Bill Gleason, Josh Meister, Mason Pearson, Jackson Tesser, and Avon Towle, please. Maybe do it right now before you forget. Take some pictures and submit that stuff into Schoology if you haven't already, because I did email everybody. But there it is. Page 237, 12 to 27, 90, 96, and 100. Feel free to stay on. You can work on it. Ask questions if you get stuck on anything. If you want to sign off, work on it, and then come pop back in and ask questions, that's cool too.